Right, this is week 6, and we have two quite short sections this week, which is good for you since you will be spending a lot of time getting ready for your semester test on Saturday. In this section 11.7, we consider the idea of how to know which test to use in which circumstance. So what we have now is, we have in the last 5 weeks or so developed a number of tests that allow us to test for the convergence or divergence of a particular series. Now you face the problem of knowing which test to use under which conditions. And unfortunately, there is no hard and fast rule. So the best we can do is to give sort of general direction, general ideas on how to approach the problem. And the crux of this direction that we are going to use for tackling a particular problem is to look at the form of the problem. So you need to have a look at what the actual series looks like, and based on what it looks like, it should trigger memory of a particular approach that we did in the first 5 sections. And so let's look at these general pointers, and then look at very briefly at specific examples. So the first one, if the series has the form the sum of 1 over n to the p, then obviously it's a p series, and we know the conditions under which p series converge and diverge. Specifically, we know that a p series will converge if p is greater than 1, and that it will diverge if p is less than or equal to 1. Secondly, the second kind of series, actually the first kind of series we looked at, was a geometric series. Again, this form is well known to us, and so if the series has form the sum from 1 to infinity of a times r to the n minus 1, or the sum from 1 to infinity of a times r to the n, then it's a geometric series, and again we know that it will converge if the absolute value of r is less than 1, and it will diverge if the absolute value of r is less than or equal to 1. For this last one, remember that it may be necessary that you need to do some algebraic manipulation to get the problem that you are presented with for it to become clear that it's in fact a geometric series. If the series has a form that resembles a p series or geometric series, if one of these two happens, then the comparison tests should be considered. In particular, if an is a rational function or an algebraic function of n, then the series should be compared with the p series, and the value of p should be chosen in accordance with section 11.4. And by that we mean, if you go back and look at 11.4, we kept the highest powers of n in the numerator and denominator to construct this new test series, the series with which we are going to compare the given series, the series in the given problem. Also keep in mind that the condition for using the comparison tests is that all of the terms in the series must be positive. If the sum of an has some negative terms, then the idea is to look at the sum of the absolute values and see if you can get absolute convergence. And remember that absolute convergence implies convergence, but not the other way around. If you can see at a glance that the limit as n goes to infinity of an is not 0, then the test for divergence should be used. In fact, I'm tempted to say that I would always try and use the test for divergence first. If the series has form -1 to the n minus 1 times bn, or the sum -1 to the n times bn, then the alternating series test is an obvious possibility. If the series involves factorials or other products, including a constant raised to the nth power, then you should consider using the ratio test. Here, keep in mind that the absolute value of an plus 1 divided by an will always converge to 1 if the p-series is for a rational algebraic function of n. If an has form bn raised to the power n, then you should consider using the root test. And finally, if an is equal to f of n, where we can take this function f and extend it to become a continuous function which is defined for all real numbers larger than 1, and it's the case that the improper integral from 1 to infinity of f of x dx is easily evaluated, then you should use the integral test, assuming that the hypotheses of the test are satisfied. Okay, let's look at some examples. Look at this one, the sum from 1 to infinity of n minus 1 divided by 2n plus 1. As I said a minute ago, I would almost always try and use the test for divergence first. And in this case, if we calculate the limit as n goes to infinity, we see that it's equal to a half. And remember, we calculate that limit for the nth term, right? And so we need to calculate the limit as n goes to infinity of n minus 1 divided by 2n plus 1. That goes to a half, and so we use the test for divergence, because the test for divergence says if it's the case that an does not converge to 0, then the series cannot be convergent. The next one, the sum from 1 to infinity of the square root of n cubed plus 1 divided by 3 times n cubed plus 4n squared plus 2. Here, an is an algebraic function of n, and so we try and use a p-series. To construct the p-series that we're going to use, we look at the highest power of the variable in the numerator and the denominator, and we ignore all the rest and we construct our bn in that way. And so we say let bn be equal to the square root of n cubed divided by 3n cubed, which is n to the 3.5 divided by 3n cubed, which is 1 divided by 3n to the 3 over 2. So for this problem you will go and see if comparing the given series with the series the sum from 1 to infinity of that bn actually gives you a solution. The next one, the sum from 1 to infinity of n e to the minus n squared. It's easy to see, well, if you think about it a little bit, you'll see that the integral from 1 to infinity of x e to the minus x squared dx is easily evaluated. When I look at this, I immediately think of, if I need to take the integral of that expression, of that function, then I will use u substitution, right? And my u is going to be minus x squared. So that du minus 2x dx is used to I can see that the x standing in front of the e to the minus x squared caters for that du. We use the integral test, And the ratio test will also work for that one. The next one, notice immediately that we've got an alternating series here. In other words, minus 1 to the n is the thing in the form, is the part of the form of the problem that will let me think, give me the idea that we should use the alternating series test. Example 5. The sum from 1 to infinity of 2 to the k divided by k factorial. Since the series involves k to the k factorial, we will use the ratio test. Example 6, I think this is the last one. The sum from 1 to infinity of 1 divided by 2 plus 3 to the n. Since the series is closely related to the geometric series, the sum of 1 divided by 3 to the n, we use the comparison test. And I think that's it.